different. The strong force is between the quarks. Actually, the strong force is within the nucleus of the atom. Remember, we talked about neutron degeneracy pressure in the context of neutron stars? That particular, so neutron stars are maintained by neutron degeneracy pressure. The force between the subatomic particles are, as in the subnuclear particles, are is actually the strong force. Neutrinos interact through the weak force. Electrons also interact through the weak force. The uniqueness of neutrinos is that they only interact with the weak force. If the neutrinos also interacted with photons, then they would be less elusive, but they don't. Similar thing with dark matter. We see it to not interact with photons, so we're thinking it might be kind of like the neutrino in that sense, but we would want more mass. We would need more mass. And so we thought up the WIMP. But that was a little bit of a tidbit on particles. Hopefully you enjoyed that. And if you have any questions about the particles, let me know. And it came up, I wanted to address it because of something we discussed yesterday. We were talking about the superstring theory, and it is important to understand quantum states and some basic information about quantum mechanics, because it will come up when we further discuss superstring theory. Because remember, superstring theory's motivation is to be a grand unification theory, a theory that can be a broader theory that can encompass more things like particle physics, gravitation, electromagnetism. So, and particle physics meaning including quantum mechanics, of course. Quantum mechanics success leads to particle physics. So if you're going to understand superstring theory, which is a requested topic on this channel, we have to keep in mind that when we discuss it, we have to keep in mind that it has to explain quantum mechanics and particle physics. And that's why I wanted to talk a little bit about quantum mechanics, and somebody had asked yesterday about the quantum states and spin. And spin is a quantum property. It's one of the states or properties of a particle. When identified, it helps you with the identity of that particle. Other such properties being mass and charge. It's like asking 20 questions or playing Guess Who. If I told you the mass, the charge, the spin, you could tell me you're talking about the electron, or you're talking about the photon, or you're talking about the W boson. Okay? Is that helpful, Reese? Is light a wave or a particle or both? It's both. Light has wave-particle duality. Let's talk about that. Light has wave-particle duality. Now, so light is both a particle and a wave. At long wavelengths, light is more like a wave. And at short wavelengths, light is more like a particle. What do I mean by that? As you know, light is possible to be found in various wavelengths, and or same as saying various frequencies. Longer the wavelength, shorter the frequency. Because the speed of light in vacuum is a constant. So since wavelength and frequency, the product of that will give you the speed of light in vacuum. Those are kind of they're inversely related. Longer the wavelength, shorter the frequency, smaller the frequency. So for example, radio waves are longer wavelength type of light. Radio waves are still light. Microwave, my microwave that cooks most of my food, is still light. Visible light, which most of our eyeballs can only see visible light, that's still light. UV rays from the sun is still light. Gamma rays from certain astrophysical events that I like very much are still light. X-rays that are needed in the hospital are still light. These are all types of light. It's the same light, it's still light, but it has different wavelength. It's a different wavelength or a different frequency of light. So when you ask, does light have wave-particle duality? It does. It has wave-particle duality.